So we move forward in time we're going to ask the question, what is relative age dating? What you see in the photograph here is an area along the south coast of Wales, which you're going to understand the significance of the country Wales by the time you end this class, if nothing else. These are Jurassic rocks. They're not sediments, they're rocks. They were once sediment that were solidified, lithified, if you will, and turned to rock, and they're limestones. In fact, it was a time when Wales was at a much more equatorial sort of latitude. And so this is Wales with limestone and shale, and that's caught in a little graben-like structure right there. So that is a structure right there. But what this illustrates is that there's one layer was deposited on sediment that was deposited on another layer of sediment, and so forth, repeatedly through history. And so it's an incredible place to visit if you ever get a chance. The coast path along Wales runs right through here, and fascinating rocks, Jurassic age rocks, sitting on top of an unconformity. Actually is missing time. And so on the right hand side there, you can actually see the lower Carboniferous exposed there, and I think a tiny bit of the upper Carboniferous up in the middle part of that sandwich of rocks, if you will, right at the edge of this structure. So interesting that way. So last time we were talking about time, and now we're going to talk about relative time, if you will. And it was Arthur Eddington who came up with the idea that time is an arrow, and he called it time's arrow. It only shoots in one direction, towards the future. Now, even though that's the case, we also know from our experience as humans that there is what we call a past. And of course, we live in the present and we look forward to the future, if one's coming for us, hopefully. And so those are the three parts of this time bubble that we are in. And today, in the presence, in the present tense, if you will, is that sort of edge of the bubble as we continue on into the future. And now we're in the future. There's an old song by They Might Be Giants. It's called Now You're Getting Older, and Now You're Getting Older. And so it's we keep going forward in time. That was Eddington in 1927 who recognized that. And so with that in mind, we know that there's a past. Okay, we can make predictions about the future based on what we know about the past. And so in the physical sciences, it's a little bit different than what we have in the social sciences and social science. Of course, we have history and we have our anthropology and archaeology and so forth. But in the physical sciences, we have geology and paleontology that help us with this. And we deal with the past based on this. And so we're really looking at a sequence of events in time. And so we could say that one happened earlier, and then one happened later, and then another one may have happened even later. And so that's kind of the way that we structure our understanding in relative time. And so it doesn't tell us anything about the absolute time, like what time is it right now? Well, you can look at your watch and find out, or you can look at your cell phone now and find out. If we look for examples in this, some great examples would come from the sport of baseball. And so here is a photo, an image, if you will, of a scoreboard, right? Out in left field or right field, they're going to have a scoreboard out there. It may keep track of balls and strikes and how many outs there are in that inning. And then they also keep track of each inning scores. And so each inning scores, and very often, of course, they expand that and they'll have runs and hits and errors added to this as well. But in this case, it's a fairly straightforward, and they just give you the visitor. The visitor always bats first, right? And so the visitor and then the home team after that. And you can see in this illustration, well, first of all, who won? Okay. The team that won is the home team in this situation, right? What was the score? It was 10-6. That's over on the right-hand side there, right? So that's who won, but who scored first? The team that scored first is the visitors' team, and they scored one run in the first inning. And then the home team scored 2 runs after that, right? So, but in what inning or innings did the home team outscore the visitors? And so, well, they outscored them in the first inning, they outscored them in the 5th inning, and then they outscored them in the 8th inning. So you can actually just do the math on this: 2-1, 2-0, and then 2-1. On each one of those, they actually outscored the visiting team. How many innings? What inning did the winning run actually get scored? So, well, if there's 6 runs that were scored by the visitors, what was the inning that they scored the 7th run? And that would have been the 6th inning in this situation. So they scored their 7th run, and the 6th inning would have gone ahead, and they kept the lead ever since. And so they even scored 3 more runs after the 6th inning, and so that gave them a total of 10. What time was the winning run scored? Well, that's almost impossible to tell from this data, right? Well, it is impossible to tell. We don't know if this is an afternoon game or an evening game, and we don't even know what time, like the 6th inning, was played. So there's no way to know. And so in other words, a score board like this in baseball is an example of relative time. There's a sequence of events that occurred in this game, and we can kind of make some sense out of how the game progressed, but we have no idea in detail how it did or at what time it did. And the reason I even mention this is because the geologic timescale is the same sort of thing. When the geologic timescale was developed, nobody had any idea about what the real time was that was involved with each one of these periods. And so that came around much, much later. In fact, it's gotten better and better. That's the absolute age dating that we're going to talk about in the next lecture. So if we go on to the next slide, you can actually see that even in baseball, you can do a much better job of seeing the relative time scale in real time. Essentially, you're witnessing the game and recording what's happening. You can record hits, runs, and errors, stolen bases, RBIs, all of these sorts of things, and you still don't have the timestamp on it that tells you exactly when these things occurred, and you don't know what the duration is of each inning and so forth, unless you're absolutely intent on recording the time as well. And of course, you can do that with video, of course. But so here is it's a much more detailed relative time scale. And that's the way that geology developed as well. We had a basic understanding back in the late 17th, and actually it starts in the late 1600s. So in the 17th century, the late 1600s, 1680s, 1690s, and then eventually we get into the 1700s, and the 1780s is the next major leap forward. And then again in the early 1800s, and we developed and began to develop the geologic timescale at that time. And so the timescale flourished and developed, but if you're around in 1830, you would have had no concept of what absolute ages of the Earth would be. And that took a lot of years later to come up with different schemes in order to try to figure that out. So that's the difference between absolute and relative time when it comes right down to it. Now, given that, we have a pretty good record on Earth. The stratigraphic column is something like a book. It's laid on its edge, if you will. And places like the Grand Canyon are kind of the best places to actually witness that book. And here in this photograph of the Grand Canyon, I can tell you exactly what age, on the geologic timescale anyway, for what that lower red layer is there. You see the real thick cliff that runs around the base of the red layers in this. Now, this is kind of color enhanced a little bit here, but that red layer down there, it's called the red wall limestone. And the red wall limestone, as it turns out, is lower Carboniferous in age. That's the period that it has been assigned to. And in North America, we generally just say Mississippian in age. So it's a Mississippian limestone. And we know that from its fossil content, and we can correlate those fossils around the world and definitely around much of North America. That's the red wall limestone. Below that, there's probably a little bit of Devonian and and definitely some Cambrian down below that as well. What you're missing here is most of actually all the Ordovician is missing here. It's a lot of the Silurian and a fair amount of the Devonian are missing here as well below the Mississippian. But you get a fair succession of Cambrian age rocks here. But above that red wall limestone, then you get into the upper Carboniferous and you get into the Supai group. And so there's a whole succession of younger and younger strata as you go up in the Grand Canyon here. And so you get up and eventually into the Hermit Shale and in the Coconino Sandstone. And then finally at the very top of the canyon here, you see that white rock that's at the top of these little pyramid-like sort of features that are in that ridge that juts out across the into the canyon. That's the you can see the inner gorge down there where this is actually Bright Angel fault that runs through this, that little canyon through here, and that's Bright Angel Creek that runs through there, Bright Angel Stream, and it runs into the Colorado River down in the inner gorge down there. So, but the layer at the top up there, that white layer, lighter color layer, I should say, it's kind of tannish in color, and that is the Kaibab limestone, and it's Permian in age, and so that's pretty much the succession. It's all Paleozoic for the most part here, and it's this beautiful exposure of these rocks. You can just imagine if you took a book and each page recorded some history, and then you carved a big V into that book and took out all of the debris, if you will, that was in that V, and you got left behind with a V and all the pages that were exposed right up against the cut. Well, the canyon has cut into that book, essentially, in this case, and it left that sort of record behind. And people who study these rocks in the Grand Canyon know what ages they are. And if you visit there, it's pretty easy to learn these things as well. So those are the layers of sedimentary rock, once sediments, that are recorded in the Grand Canyon. And that's the sort of record we talk about when we talk about relative age dating. Now, it's the same sort of thing when you're doing an excavation, except you become the type of erosion that will remove some of the sediment above. And you try to record what you find. If you're in archaeology, what's at each level. And you may find middens, you may find all sorts of different artifacts in this in an excavation like this. But in fact, what you're looking at here is soils that are layered up as well. Soils are actually much more dynamic than you might think. Some soils are windblown, of course, and other soils accumulate from the weathering of the bedrock. And so they're recording, in this case, different civilizations that may have lived across this landscape. So we're going to go to, on the right-hand side over here, you can see two people, actually. One of them, I don't know who that is, but we always take photographs. We try to have people in them. We don't always have people in them, but a person gives you a sense of scale. So in other words, that outcrop along the ocean there, that's along the North Sea right there, is on the west side of Denmark, actually. And it would have been an area where this fellow named Niels Stensen would have visited at some point in his life and probably seen this. It's not the place where he made his great discoveries, but that is Niels Stensen right down here in that little inset here. And he is kneeling on one knee. He was a Catholic bishop, and he was born in Copenhagen, and he was born a Lutheran and actually converted when he was in Florence. He was a learned scientist. He went to school. He was actually most noted for his anatomy studies when he was, when he was actually a student. He learned his skills very, very accurately. And in fact, his father was a jeweler and a watchmaker. And so he was very good with a scalpel and was able to dissect things very, very accurately. And among the things that he dissected were things like sharks. Nobody really knew what sharks were until somebody caught one at one point, and he was asked to dissect it. He dissected the head of a shark and illustrated it, in fact. So anyway, this is along the coastline of Denmark here, but you can see the layers along that coastline. So he saw layers everywhere. This is a guy who would eventually become known as he's a scientist. His name was Steno. And so we're going to talk about Steno in here. Oh, probably quite a little detail. So sediments generally accumulate in more or less flat layers. That's one of the discoveries that Steno made. Now, that's common sense, isn't it? Right? It's like, of course they're coming. Well, people didn't really recognize that back in the 1600s when he was studying these rocks, and they thought that everything was just a manifestation of God's creativity. And so in his creation, he would have just made the rocks, or he would have made the soil. And it was Steno that said, no, these strata actually accumulated by natural processes, and those sediments would have been deposited in a relatively flat sort of aspect. The church dominated much of the philosophical thinking in the Middle Ages. And so he called that, of course, it became known as original horizontality. All sediments are originally deposited horizontally. In other words, they don't accumulate in a vertical sort of aspect. They're not just made that way. In other words, we're going to call upon natural processes by which these things will actually form. And he was a bishop in the Catholic Church, okay? So he was still a scientist. And so each one of the layers that you see in that cliff, they're called a stratum. Stratum means a flat layer, if you will. And the plural of that is strata. So strata means a collection of flat layers that would have accumulated. And strata, of course, can later at some time be buckled and folded and become less than horizontal, but they were originally horizontal. And so that's an idea we attribute to Steno, Niels Stensen. He had several names, actually, and people at that time, learned folks in the Middle Ages, would always Latinize their names, and so it was shortened to just Steno. And so original horizontality was one of the original concepts, one of three that he came up with. So that's number one. Okay, since the 17th century, and so when we say 17th century, we're talking about the 1600s. And naturalists began to collect and describe fossils. And really it was in the 17th, 18th century when that really came to fruition. At the very end of the 17th century and into the 18th century. And many of these fossils were regarded as just manifestations of God's creation, instead of being things that were once living. Now that's, would give too much credit to nature, I guess. Ammonites, in fact, the ones that you see at the very top up here, these sort of coiled seashells like this. Let's see, what was the guy's name who came up with this? He was a Brit, and he said he was a bit pompous, this guy, and he said, well, there's no such thing as extinct animals. Nobody would give credence to the idea that organisms could have lived and died and were no longer present on Earth. And he says, well, I've seen things like that before. And of course, he was referring to the Nautilus shell, which is a chambered shell, and he had collections of things like that. But he also collected rocks in the in areas like the Lyme Regis area of Britain, and there are tons of ammonites in there, and these ammonites are really extinct. But he says, these things, they're probably out there in the ocean. Nobody just found them yet. It's like so. And there are things like trilobites down here at the bottom. And so where do those trilobites, where are they as living creatures? Well, they don't exist anymore because they are extinct. So they didn't give credence to the idea of extinction back in the 17th and on into the 18th century. So fossils became this sort of enigma. And in fact, that's one of the things that Steno was trying to solve. Where do fossils come from, and why are they on the tops of mountains? I have to give you a heads up here. Even Mount Everest, the highest mountain on Earth, has Ordovician marine limestone at the top of it, okay? That's how pervasive that these fossils can be. They're everywhere, right? And so even on mountaintops, you can find fossils. Did that mean that the Great Flood got up there and deposited these animals? Yeah, well, you know the answer from me, but it's like that was a big puzzle to guys like Steno. So where do fossils come from? So one of the guys that came along in the late 1700s and on into 1800s, he finished his map. I think it was published in 1815. His name was William Smith. He was an engineer and a geologist, and he collected fossils all over Britain. And Britain features kind of prominently in understanding of geology, but so does Italy and a few other places that had some of these early scientists who contributed to our understanding as well. Steno, in fact, was Danish, but he felt most at home, in fact, in Florence. He was a part of the Medici Scientific Institute, if you will. It's called the Cimento. And he studied out of Florence and did a lot of travels and investigations in geology that way. And these were mostly learned men who had a lot of time on their hands, but not William Smith. William Smith actually did this as part of his job. William Smith was what they called a jobbing ditcher. And if we go on to the next slide here, you can see the map that he put together for all of Britain and Wales. And so what you see here, the dark areas on here are actually what they call the coal measures. That's places where you could actually map and find coal. And so they used maps like this in order to find resources and to make predictions about where they could find other resources. And so this is a very important map published in 1850. And it was the first detailed geologic map ever published, and detailed in a large scale, let me put it that way. Now, what he would do, he would cut ditches, and he would drain some of the swamplands across the Midland region on the eastern side, Anglesey, and then, so when he did that, he would record what kind of fossils he found there, collect them, and he made careful notes, and he eventually published this map. And he recognized that you can trace layers of sedimentary rock from one place to another. That became one of the most brilliant ideas in all of geology. And in fact, there was a book written about this one as well that was called about his life, and this is William Smith. And it was called The Map That Changed the World. And so I have a copy of this map, in fact, and it's just a beautiful illustration of the rocks that occur if you were to strip away all the vegetation and all the soils, other sorts of superficial materials that may lay across the top of the surface. You would have bedrock under that. And so this is a bedrock geologic map. And so he did what they call stratigraphic correlation. If he saw a certain rock in one area that held a certain kind of fossil, he could compare that to another place that had the same kind of fossil. And so what you see here, the areas that are in black are called the coal measures. The area below that, of course, would be part of the Carboniferous as well. And we call that the Mississippian here in the United States. But over there, it's the Carboniferous. And Carboniferous meaning, in this case, that it has carbonate material in it. And so there's a whole bunch of younger rock as you get down towards London in that area. And so he used a relative time scale again. Again, we have no idea how or what time that these rocks were actually being deposited. And it was from these early studies like this and the collection of fossils that we began to piece together this idea of stratigraphy. And of course, on the next slide, you can see, here's the geologic timescale that we come to know today. And you can see, you can find the Carboniferous on here, but it shows you where the oldest and the youngest rocks are, or the youngest time periods, if you will, as well. So it's not straightforward in some ways. It's like rocks are not the same thing as time. We just said that time is a different dimension, right? So time moves through this sort of like three-dimensional network, but those are rocks that were deposited during a certain period of time that you've seen already. And so that's why they call it a chronostratigraphic chart in the IUGS. And here they call it a geologic time scale. So they're just giving you the time element in the GSA version, and because they're actually combining both the relative time scale and then also the absolute time scale. So those are the dates that you have to remember. So that is our geologic time scale. We're going to go into this in a lot of detail, in fact, about who discovered the first rocks that were Ordovician in age. Actually, not so much the Ordovician, but the Cambrian and the Devonian, the Silurian, and then the Ordovician is an interesting case, and we'll get to look at it in more detail as well. So now you have a good understanding of what relative age dating is all about. There are other ways that people can do it as well. And so in this photograph here, well, it's actually this image. It shows you a cross-section of a marine basin, and there are little squiggly lines that run across. Actually, some of them are relatively flat and they're slightly curved, and those are called, let me make sure I get this right, those are called reflectors. That's correct. And so this is actually recorded in two-way travel time, so that's in seconds on the right-hand side, because if you have sound that goes into the rocks that are down below, and it reflects off of those rocks and comes back to you and is recorded in what we call either a hydrophone or a geophone. In this case, probably a hydrophone, since these are probably marine rocks right here. What you also see at the bottom is the interpretation of what the squiggly lines at the top are. And so very commonly we have to interpret what we see in seismicity and seismic sections, seismic profiles like this. So in this case, with rocks, if you're cutting a ditch, you only have discrete little areas where you can actually find a fossil and discrete areas where that rock may crop out. But in this case, you're looking at it more or less continuous, but still just a 2D version of what it means for these layers to actually correlate across in entire sections, perhaps, stratigraphic profile, perhaps. And so what you see at the top are the reflectors, and the interpretation is then at the bottom down here. But that's still not telling you what age any of these layers were deposited. And in fact, so they even show you that some of these are kind of chaotic in their nature as well. So that's another way to do relative age dating. It doesn't have to be just with the exposed rocks. It can also be through remote means or through indirect evidence, if you will, looking at seismic profiles. And essentially that's shooting sound into the earth and getting a reflection off of that, processing it with a computer, and then making an interpretation based off of your understanding, maybe from coring or from other sort of information that you may have about the development of sediments in a basin, the development of how sediments were deposited in the basin. And so in the next page, you can actually see where somebody has done well logs. Okay, so when they've cored this area, they can actually collect that data, and you can get other types of remote imaging sort of information, if you will. In this case, these well logs actually record electrical signals of various types, and they can correlate those from one place to another. But again, they're only doing relative age dating on this. In other words, you know what's down below and you know what's above, and you can actually spot. I hope you've already run into this word already, but we're going to run into it again in historical here. It's called unconformities. So if you find unconformities or truncation surfaces in the subsurface from coring data, you've got a pretty good handle then on some of the relative age dating. And so that's what they're showing you here. And in fact, many of the wells are actually tied into this seismic section at the very bottom down here. It's just an illustration from a scientific paper. And okay, so on to the next slide here. Another photograph from Wales. And these are slightly older rocks, I think, right here. This is from Pembrokeshire on the very southwestern tip of Wales. And you're looking here at probably Ordovician and Cambrian age rocks. So if you just look at these rocks, can you tell which ones are the oldest? Which way is up, I guess, is what I'm really asking here. And the answer is not straightforward. Okay, so how do you know what is up and what is down if you're dealing with vertical rock successions like this? So we know, first of all, that this was not deposited in this fashion, right? It had to have been relatively flat and then got upturned in some ways, uplifted. And in this case, you might make an argument that there's some cross-bedding on the far left-hand side here. It looks like some cross-bedding in there, and so maybe up is off to the left. And if that's the case, which direction would you go to find the older rocks? Well, this is another principle we're going to deal with in here, but if we can actually tell what up is in a succession of rocks like this, that stratigraphic up tells you that everything off to the right then would be older than the rocks that are on the left-hand side. And the area I'm looking at here is about in the middle of the cliff on the left-hand side, and you can kind of see where the strata are kind of folded, if you will. It looks like either they're cross-bedded or maybe they're folded there. I'm guessing that you see how it kind of, the bed kind of like stops there as well. So it may be part of a channel fill succession, if you will. So my guess would be off to the left would be the up direction, and to the right as the older rocks. Now, in this case, another thing to point out here, we have a lot of indicators that tell us what up is in the geologic sense. And we have a special name for that, and you're going to see it again at some point in your career. Maybe not in this course, but you will actually find it in stratigraphy and those things that, for instance, if you found a seashell in there and that seashell was partially full of sediment and then completely occluded on the other side with cement, okay, so half sediment, half cement, we know that the cement probably formed after the sediment partially filled in that shell. Those things are called geopetals. Geopetals, Geopetals. So they're way up indicators, in other words. So we know that also that when rocks are not originally deposited in a vertical manner like this, there must have been some sort of mountain building event that caused these things to occur. We call that orogenesis, right? So oro meaning mountain and genesis meaning the beginning of. Okay, so it's difficult to know what the up direction is. I can only make speculations in this case. So we go on to the next slide here, and this is from one of the more sacred spots in geology, if there is such a thing. These rocks are actually from Scotland, and this is a place called Siccar Point. It's one of the more famous locations in geology. And it was here that James Hutton came up with the idea that rocks can cut other rocks, and that unconformity shows that there's a deep time that's illustrated in the geologic record. And so you can see that the rocks are vertical in the foreground here, and then the rocks over the top are slightly inclined, okay, but they cut the rocks from below. Well, the rocks in the lower part are part of the Silurian, that's the Gala supergroup. And then they're mostly mudstones, and not lime mudstones, but just like a mudstone and like a dirty sandstone, if you will. Not really shaly, though. And then there are sandstones above, and those are Devonian in age. And so Silurian overlain by Devonian in this case, and that's an unconformity between them. That's going to be known as an angular unconformity. It's the world's most famous unconformity, I guess you could say, because James Hutton, it's a story in and of itself, and we're going to talk about him later anyway. But anyway, so you had to have some uplift on those Silurian rocks, and then you had to cut them by Devonian time. So that's called a cross-cutting relationship in this situation. So, okay, so on to the next slide, and this is going to be, it shows you what we base most of our understanding of the geologic record from the absolute age dating, where that comes from. And it's mostly from fossils, as it turns out. And so these fossils on the right-hand side, it says invertebrate fossils, and it shows you some brachiopods actually right here. And it gives you some of the geologic timescale on the left-hand side over here. Those are the more key components, if you will. But it also gives a rank too. So that's pretty important, I guess I would say. You need to know more than that. So I've given you that entire sheet to learn. But that's our language that we're going to talk about in this class. So I think that's pretty much it for this, as far as just explaining what we're going to be talking about. Let me just show you some photographs of some spectacular places next here. So in the next photograph, you can see Lower Cambrian rocks. They're mostly quartzite in this situation, so they've been slightly metamorphosed, but you can still see cross-bedding and ripples and things like that in there. And that's part of the Prospect Mountain quartzite. Crops out in the Snake Range in eastern Nevada. And so eastern Nevada, that's the highest peak in Nevada right there. That's called Wheeler Peak on the right-hand side. It looks like it's flat top, but it's actually kind of a knife edge at the very top. Oh, maybe 30 or 40 feet wide. Climbed it several times, in fact. On the left-hand side, you can see Jeff Davis Peak, and it's made out of the same quartzite there. Very rugged, very rough, and I don't know of anybody that's climbed that, although I'm pretty sure that somebody probably has tried to climb that. It's a walk-up, though, to get to the top of Wheeler Peak. Yeah, not an easy walk-up, I wouldn't say, but it's a walk-up, and it's just it's a wonderful place to visit if you ever get a chance to go out there. This is part of the Great Basin National Monument. Great Basin National Park, I guess it is now. And in the foreground here are some 3,000 to 5,000-year-old trees. And those are called bristlecones. And so just to dispel any sort of idea that you think that you may reconcile an age of about 6,000 years for the age of the Earth, no. These mountains are really old, and the trees are really old too. Okay, so everything's kind of old in this photograph. So that is the Snake Range in eastern Nevada. And this is in western Utah, the next slide here, and you can see a whole succession of middle and upper Cambrian carbonates in this case. So that's limestones and dolomites and a little bit of shale in there too, but mostly limestone. And what you see here on the left-hand side, it's called the, let me get this right. I think it's called Eye of Needle limestone there. And on the right-hand side, you can get the up in the Notch Peak Formation, I think it's called. But this is on the west side of the Wawa Mountains. And if you were to cross over the mountain pass that we're on here, you would have a direct view of the Snake Range in the distance there in Nevada. So this is on the west end of Utah. I've done a lot of work out there with some other folks. There's roughly 10,000 feet of Cambrian age rocks exposed here. Now in the Snake Range alone, there's probably about 3,000 feet of the Prospect Mountain quartzite there. And the Prospect Mountain quartzite actually is exposed at the base of a cliff on the other side of this pass. And so it just shows that you can stack a lot of rock if you have the right sort of situation. So there's over 12,000 feet of these rocks that are Cambrian in age in this part of the world. Well, it was at the edge of North America at that time. It wasn't even called North America at that time. That's a human construct, right? Language, right? And so, in fact, even as humans, we call this Laurentia at that time. It's the ancient continent of North America. So here we have the Cambrian succession and the western edge of Laurentia. Okay, on to the next slide here. Maybe you've driven to Colorado before. Maybe you've driven up into the mountains. And as you leave Denver's out in front of the mountains, of course. And as you leave on Interstate 70, as you climb up into the mountains, you'll pass by this sort of exposure right here. They built that road right through this thing, and that's called Dinosaur Ridge. And the reason they call it Dinosaur Ridge is because they find dinosaur bones, and they also find dinosaur tracks in some rocks that belong to the Jurassic there. So you're familiar with Jurassic Park. Well, on the right-hand side of this image, you can see that there's a little railing up there, and maybe some people even, as you see on the right-hand side of that photograph there, those gray rocks in there, that's a shale. That gray shale belongs to the Morrison Formation. It's named for Morrison, Colorado. And above that, you get Jurassic, and then eventually you get into Cretaceous age rocks on the far left side here. Now notice that these rocks are tilted, right? That means there had to have been some sort of mountain building process that tilted those rocks after they were deposited. These rocks were deposited then in the Jurassic, and then they were deposited in the Cretaceous as well. Now the Triassic, if it were around here, would be off to the left-hand side, slightly older, right? So the young direction goes to the left in this image here. But those are marine rocks. Even the Cretaceous are marine sediments. And so the Cretaceous had seas that were in central Colorado during Cretaceous time. But then sometime after that, a mountain building event occurred. And it brought rocks up from Precambrian time all the way up to the surface. And so that was the building of the Rocky Mountains. And so the mountain building event itself postdates the deposition of the rocks that compose part of the sediments around it. Doesn't postdate, well, there are Precambrian age rocks involved in the core of the formation of that mountains, but these are younger rocks. And so they had to be, the mountain building event had to be younger than Cretaceous, in other words. And so these rocks were deformed, actually in the very, very latest Cretaceous and on into the Tertiary. So that is Dinosaur Ridge. Those are Mesozoic age rocks, the kind that have dinosaurs in them, right? Around here, we have rocks that are mostly Paleozoic in age for the most part. And here you can see a quarry that was put in around Branson to feed the construction industry, right? So you can make gravel out of this. They make what they call aggregate as well. So you can make concrete from these rocks. And so at the very bottom here, you have lower Ordovician age rocks. There's an unconformity that runs across the middle of that shelf, about 2/3 of the way up. There's an unconformity. It doesn't show any angular discordance, so it's called a disconformity. And above that, you get Mississippian age rocks. And so if I tell you it's lower Ordovician at the bottom here and Mississippian at the top, Well, you're missing then the upper Ordovician, you're missing the middle Ordovician, you're missing the upper Ordovician, you're missing the Silurian, you're missing the Devonian, and finally get in the Mississippian age rocks above that. They're all marine rocks for all we know here, right? So these are all marine for the most part, but there's actually probably 100 million years missing right at the base of one of those ledges. And so that's pretty profound. And so we call that around here, we call it the sub-Mississippian unconformity, very profound surface across the mid-continent region, southern mid-continent region. On to a summation of what you've seen so far. You've seen a succession of illustrations now that kind of show you what we know a little bit about different areas in the relative age dating of rocks. You've learned about original horizontality. You will learn about superposition soon enough, and you're going to learn more about unconformities as well. And then you've seen examples of really thick successions of sedimentary rocks. And there's not a bit of this that tells you what time it was on the clock when that was deposited. So all of this is based on relative age dates. Much of our understanding of Earth is based on relative age dates, based on the fossil content, based on the rock successions that we see from place to place. And so people have been studying this type of geology for the last 200 years here. Even in Missouri, it started about 1840s when people began to look at the geology of Missouri. So, fascinating story that we have to tell, and I will speak to you soon about absolute age dating. All right, thanks a lot. Bye.